Have you ever looked at the world and felt like it makes absolutely no sense, and yet somehow still follows rules? That strange feeling is where our story begins. The universe around us looks chaotic at first glance. Waves smash endlessly against the shore, clouds form and dissolve without warning, and trees bend and whisper under invisible winds. Everywhere you look, there's motion, noise, color, and unpredictability. It feels messy, almost random. But deep down, most of us carry a quiet suspicion that this chaos isn't truly random at all. Beneath the surface, something orderly must be happening. Some hidden system, some structure, some rules. Imagine for a moment that the universe is like a massive chess game being played by unseen players. The board stretches infinitely in every direction, so we can't see its edges. The pieces are tiny, so we can't fully make them out. And worst of all, nobody told us the rules. All we can do is sit in the audience and watch as moves unfold. A piece shifts, something reacts, patterns appear. We lean forward and try to guess what just happened. Maybe when a pawn moves 2 squares, something special can happen next turn. Maybe there's a rule we're starting to notice. This act of watching, guessing, testing, and refining our understanding, that's what we call physics. It's humanity trying to reverse engineer the rules of a cosmic game we never signed up to play. But here's the unsettling part, the part that keeps thinkers awake at night. The rules we discover, the formulas we write down, the predictions we make, they're all written in mathematics. And mathematics is something we invented. We defined numbers. We decided what shapes are. We created calculus to track change. These ideas exist in our minds, like tools we crafted to understand the world. So why does the universe, which existed long before us and doesn't care about our notebooks, obey the very language we made up? It's a mystery that's easy to overlook but impossible to fully answer. You could imagine a universe where events happen without patterns, where laws shift unpredictably, where cause and effect don't exist. But that's not the universe we live in. In our universe, if you write the right equation, you can predict where a planet will be centuries from now. Engineers can calculate whether a bridge will stand. Scientists can forecast how atoms behave. It almost feels as if the universe itself understands math. Or maybe math is simply the only language it ever speaks. But that raises another question. If we invented mathematics, how can it describe reality so perfectly? Clearly, we didn't invent the universe. So somewhere, there's a deep connection between the logic of nature and the logic of human thought, a connection we still don't fully grasp. To understand how we got here, we have to rewind thousands of years. Long before modern science, ancient civilizations were already watching the skies. The Babylonians, for example, became remarkably skilled at predicting when the moon would rise or when the sun would set. They tracked patterns, built tables, and relied heavily on numbers. They didn't have geometry or theoretical models of the cosmos. They simply recorded what happened and used repetition to forecast the future. Other cultures did similar things. The Maya, for instance, could predict eclipses with astonishing accuracy, yet they didn't know the Earth orbited the sun or that the planet was even spherical. They weren't building physical theories. They were mastering patterns. Then came the Greeks, and everything changed. Unlike earlier astronomers, the Greeks loved logic. They believed that if you started with a few undeniable truths, you could build an entire system of understanding from them. They explored geometry, created axioms, and proved theorems using pure reasoning. Instead of studying the world directly, they studied ideas. They imagined shapes, lines, and angles, and from those mental constructs they built an elegant mathematical framework that felt timeless and universal. And centuries later, that framework would become the foundation for one of the most important insights in human history. And centuries later, that framework would become the foundation for one of the most important insights in human history. Enter Isaac Newton, a man who looked at the ordinary and asked an extraordinary question. People had seen apples fall from trees forever, and they had watched the moon glide across the sky just as long. These seemed like completely different events. One was a simple drop toward the ground. The other was a graceful, endless motion overhead. Nobody seriously thought they were connected. Newton did. He wondered whether the same force pulling the apple downward might also be responsible for keeping the moon in orbit. Today we call that force gravity, and it feels obvious. But at the time it was a radical leap. The motions didn't look alike. One was straight and abrupt, the other smooth and circular. Newton used mathematics, the geometry inherited from the Greeks, and a brand new tool he invented called calculus, to bridge that gap. What he discovered was astonishing. If you assume that gravity weakens with distance in a very specific way, following what's called an inverse square law, then the math predicts the moon's orbit perfectly. The rule is simple. Double the distance, and the force drops to a quarter. Triple it, and it falls to a ninth. Gravity spreads outward like light from a bulb. As the energy expands over a growing sphere, its strength thins according to the square of the distance. It's elegant, clean, predictable. Newton captured all of this in one compact equation. The gravitational force equals a constant multiplied by two masses divided by the square of the distance between them. It's the kind of formula students memorize in school without realizing its implications. But think about what it really says. It means every object in the universe pulls on every other object. Right now, you are tugging ever so slightly on the chair beneath you, on the person across the room, on the moon above you, even on distant galaxies. The forces are tiny, but they're real. And this one simple equation lets us calculate planetary orbits, predict ocean tides, and even guide spacecraft across billions of kilometers. So the obvious question arises, why is the rule so simple? Why doesn't gravity depend on color or temperature or the time of day? Why just mass and distance? Physical laws seem to carry a kind of beauty, a simplicity that mathematics captures perfectly. But here's where we have to be careful. The equation isn't the thing itself. Mathematics describes reality, but it isn't reality. Think of it like keeping score in a game. The numbers track what's happening, but they aren't the players on the field. You could even rewrite Newton's theory in a bizarre way and say invisible angels push planets toward the sun. If those angels followed the same inverse square rule, the math would stay identical and the predictions would still work. The only difference would be that you'd now have unnecessary angels cluttering your explanation. Scientists use a principle called Occam's razor to shave off those extra assumptions. We prefer the simplest explanation that still matches the evidence. Still, even Newton's elegant picture had a problem. His gravity acted instantly across space. If the sun suddenly vanished, his equations implied the Earth would respond immediately. That didn't sit well with later scientists, especially once we learned that nothing, not even information, can travel faster than light. That's where Albert Einstein stepped in and rewrote the story once again. He proposed something profoundly different. Instead of thinking of gravity as a force pulling objects together, he suggested that massive objects bend space and time themselves. Imagine space not as an empty stage, but as a flexible fabric. Place something heavy on it, like the sun, and the fabric dips into a curved valley. The Earth isn't being pulled by an invisible rope. It's simply moving along the curved surface created by the sun's presence. It's like an ant walking on an apple. The ant thinks it's moving straight ahead, but from our perspective, it's circling the fruit. Space itself is curved, and objects just follow that curvature. But here's the twist. To describe this curved spacetime, Einstein had to rely on a sophisticated branch of mathematics called differential geometry, a field developed decades earlier by mathematicians who were simply exploring abstract ideas for fun. They weren't trying to describe gravity. They were just playing with logical possibilities. And yet, when Einstein searched for a way to explain the universe, their abstract math turned out to be exactly what he needed. Which makes you wonder, did mathematicians invent these ideas, or did they discover something that was already written into the universe itself? And just when it seemed physics couldn't get any stranger, scientists began peering into the microscopic world, where the rules start to look completely different. And just when it seemed physics couldn't get any stranger, scientists began peering into the microscopic world, where the rules start to look completely different. At the smallest scales of reality, our everyday intuition stops being useful. In the quantum world, particles don't behave like tiny billiard balls, and they don't behave like smooth waves either. They act like something else entirely, something we struggle even to describe in plain language. Physicists call these behaviors quantum amplitudes, but a simpler way to picture them is as little arrows, each carrying both a size and a direction. Imagine you're tracking a photon, a particle of light, traveling from a lamp to a mirror and then into your eye. Common sense tells us it should take the shortest, straightest route. That's how objects behave in our everyday world. But quantum physics tells a different story. According to the theory, the photon doesn't choose one path. It explores every possible path. It can zigzag wildly, loop in absurd directions, or even take routes that seem ridiculously indirect. In the language of quantum mechanics, every possible path contributes to the final outcome. For each path, we assign one of those little arrows. The arrow's length relates to the probability of that path contributing, and its direction depends on how long the journey takes. You can imagine a stopwatch ticking as the photon travels. For longer routes, the stopwatch spins many times. For shorter routes, it spins fewer times. That spinning determines the arrow's direction. Now comes the surprising part. To figure out what we actually observe, we add up all these arrows. We place them tip to tail, one after another, forming a long chain. For the wild, complicated paths, the arrows point in nearly every direction imaginable. Some cancel others out, like forces pulling against each other. When summed together, they effectively disappear. But for paths that take nearly the same time, especially those near the straight-line route, the arrows tend to align. Instead of canceling, they reinforce one another, producing a strong combined result. That's why light appears to travel in straight lines. It isn't because nature chooses the straight path. It's because all the other possibilities cancel themselves out. The straight path is simply where the contributions add together most strongly. This idea is known as the principle of least action. It doesn't mean nature is lazy. Rather, it means nature explores everything at once, and what we see is the result of interference among all those possibilities. Describing this process requires mathematics that feels almost unreal. Quantum mechanics relies heavily on complex numbers involving the square root of -1. On the surface, that sounds absurd. No real number multiplied by itself gives a negative result. You can't have the square root of negative apples or negative distances. Mathematicians invented these numbers purely to solve certain equations. They seemed like abstract bookkeeping tools, nothing more. And yet, without these imaginary numbers, quantum theory simply doesn't work. The equations fall apart, predictions fail, experiments disagree. Somehow, this fictional mathematical idea turns out to be essential for describing the behavior of electrons, photons, and atoms. In a very real sense, the universe operates according to mathematics we once thought existed only in our heads. That realization leads to an uncomfortable but fascinating conclusion. Mathematics isn't the universe itself. It's more like a map. A map can guide you to a destination with incredible accuracy, but the ink lines aren't the roads. They represent the roads. Similarly, equations describe patterns in nature, but they aren't the physical objects themselves. And lately, physicists have started noticing cracks in the map. When we push our theories to extreme conditions, especially in quantum physics, the math sometimes produces answers that make no physical sense at all. We calculate certain quantities, like the energy of a particle, and the equations spit out infinity. But infinite energy in a tiny particle is nonsense. It's not just unlikely, it's impossible. So physicists use a clever trick called renormalization. In simple terms, they subtract one infinity from another in a carefully structured way, hoping to isolate a finite value underneath. It sounds like mathematical sleight of hand, and in some ways it is. Yet after applying this method, the predictions match experiments with astonishing precision, more accurate than almost any other scientific theory ever tested. So we're left with a strange situation. Our mathematical tools involve imaginary numbers, infinities, and abstract tricks, and yet they describe reality with breathtaking accuracy, which raises an unsettling possibility. Maybe our equations don't reveal what the universe is, only how it appears from our limited perspective. To understand that idea better, it helps to think about slicing something much more ordinary. Imagine you have a sausage in front of you. If you cut straight across, you get neat circular slices. Cut at an angle, and the slices turn into ovals. Slice lengthwise, and you end up with long strips. Each cut reveals a different shape, a different cross-section. But none of those slices alone tells you what the sausage truly is. They're just views of the same object from different angles. That's a useful way to think about physics. Reality might be the full sausage, the complete structure of the universe. Our mathematical descriptions are just the slices. We have equations that describe circles, ovals, and lines, and they work beautifully for the situations we observe. But those formulas don't necessarily reveal the substance underneath. They describe appearances, patterns, and relationships, not the ultimate nature of things. Relativity gives us a powerful example of this. Einstein showed that space and time aren't separate ingredients of reality. They're woven together into a single four-dimensional structure we call space-time. Instead of time ticking independently and space sitting still, the two mix together depending on how you move. Your motion determines how you slice through that space-time sausage. When you move slowly, your slice through space-time looks different than when you move close to the speed of light. That's why time appears to slow down for fast-moving objects. It's not that clocks malfunction. It's that motion changes the angle at which you cut through the structure of the universe. The mathematics describing this effect, known as the Lorentz transformations, predicts these changes with extraordinary accuracy. Satellites, particle accelerators, and high-speed experiments confirm it again and again. But notice something important. The math tells us exactly how those slices behave, yet it never reveals what space-time itself is made of. It gives us the geometry, the shape of the cuts, the relations between measurements, but the deeper substance, the full sausage, remains hidden. This is one of the limits of human knowledge. We understand patterns remarkably well. We can uncover rules, predict outcomes, and model systems with astonishing precision. But knowing the rules of the game doesn't necessarily mean we understand why the game exists or what the board is made from. Maybe that's not a failure. Maybe it's simply the nature of inquiry. After all, the fact that our minds, evolved on a small planet around an ordinary star, can discover laws that govern galaxies and atoms is already extraordinary. Using symbols invented in our heads, we can predict eclipses centuries in advance, calculate the behavior of subatomic particles, and estimate the lifespan of stars. That alone is one of humanity's greatest achievements. Still, the search continues. Physicists dream of finding a final, unified law, a single equation that ties everything together, something elegant enough to fit on a t-shirt, yet powerful enough to explain every force, every particle, every interaction. Maybe such a theory exists. Maybe it doesn't. Perhaps nature is more like an onion with endless layers. Each time we peel one away, we uncover another beneath it. We discovered Newton's layer, where forces govern motion. Then Einstein revealed a deeper layer, where geometry shapes gravity. Then quantum theory exposed a stranger layer still, filled with probabilities and interference. There may be more layers waiting below, mechanisms we haven't even imagined yet. Maybe electrons hide structures within them. Maybe entirely new principles govern reality at scales we haven't reached. Whatever the ultimate truth is, whether there's a bottom layer or an infinite series, we rely on one guiding tool to explore it: mathematics. It's the flashlight we carry into the darkness. We forged it ourselves, shaped it from logic and imagination, and somehow it fits the lock of the universe almost perfectly. And that connection becomes even more striking when we look at something as simple and as beautiful as a rainbow. And that connection becomes even more striking when we look at something as simple and as beautiful as a rainbow. When most people see a rainbow, they see color and wonder. A poet might describe it as a bridge across the sky or a symbol of hope after a storm. There's nothing wrong with that. Beauty doesn't lose its meaning just because we understand it. But a physicist sees something else layered beneath that beauty. They see sunlight entering droplets of water, bending as it slows, reflecting inside, and bending again as it leaves. They see angles, wavelengths, and geometry. They see mathematics unfolding in the air. Does that make the rainbow less magical? Not at all. In many ways, it makes it more profound. Because now the rainbow isn't just a fleeting visual trick. It's a visible expression of the same physical laws that make stars burn and atoms bind together. The same mathematics shaping the arc in the sky also governs the structure of your body, the behavior of light, and the evolution of galaxies. The beauty isn't diminished by explanation. It's amplified by connection. And that connection includes you. Every atom in your body follows these same mathematical rules. Your thoughts, your memories, your emotions. They all emerge from patterns of electrical signals and molecular interactions governed by physical law. In a very real sense, your consciousness is a process unfolding inside a system that mathematics can describe. Yet here's the remarkable part. You're aware of it. The universe has produced beings capable of reflecting on the very laws that shape them. That realization alone turns science into something deeply human. We're not outside observers looking in. We're participants in the system we're studying. We're bundles of atoms trying to understand atoms. And somehow, through equations and experiments, we've learned to uncover pieces of the grand design. Of course, we may never uncover the entire picture. The universe might always hold secrets beyond our reach. There could be aspects of reality fundamentally inaccessible to our senses or instruments. Maybe there are limits to what any mind, human or otherwise, can fully comprehend. But that doesn't make the search pointless. In fact, it makes it thrilling. Think of science not as a destination, but as a detective story. We gather clues, test theories, and occasionally solve small parts of the puzzle. Sometimes we think we've found the answer, only to discover deeper questions waiting beneath it. The excitement comes from that chase, the moment when a new connection appears, when an equation suddenly explains something that once seemed mysterious. That's the real reward. Not certainty, but discovery. So instead of seeing mathematics as dry or intimidating, try to see it differently. Think of it as the hidden language woven into nature. It's the grammar behind motion, the rhythm behind light, the structure behind matter. In a way, it's like music, a system of notes and patterns that, when combined correctly, reveal something beautiful and meaningful. And the most fascinating part is that we created those notes ourselves. Humans invented the symbols, the numbers, the methods. Yet when we use them, they resonate with the universe as if they were always meant to fit. It's like discovering that a melody you just composed somehow matches a song that's been playing quietly in the background all along. That realization should change how we look at knowledge, curiosity, and even education. Mathematics isn't just classroom work or abstract puzzles. It's one of the keys to understanding the deepest workings of reality. And the more we learn, the more one truth keeps revealing itself. The universe is far stranger, far richer, and far more structured than it first appears. Which is exactly why we must keep asking questions. Curiosity is the engine that drives everything forward. Every discovery we've made, from gravity to quantum mechanics, began with someone looking at the ordinary and refusing to accept it as obvious. Someone noticed an apple fall and wondered why. Someone watched the sky and asked how. Someone studied light and asked what it really was. Progress didn't come from having answers. It came from refusing to stop at the first explanation. That spirit of questioning is what transforms science from a collection of facts into a living, breathing pursuit. The world around us isn't fixed in our understanding. It keeps revealing deeper layers the more we investigate. What once seemed simple turns out to be complex. What seemed random reveals patterns. And what seemed permanent sometimes dissolves into something even more fundamental. The universe, in that sense, isn't just a place we inhabit. It's a puzzle we're constantly decoding. Every new theory is like uncovering another piece. Sometimes those pieces fit beautifully with what we already know. Other times they force us to rethink everything. Newton's laws felt complete until Einstein showed they were only part of the story. Einstein's relativity reshaped our view of space and time, yet quantum theory revealed an entirely different layer beneath it. Each breakthrough didn't close the case, it opened new mysteries. And maybe that's exactly how it's supposed to be. If we ever reached a point where every question had a final answer, where every phenomenon was fully explained, the journey would end. The game would be finished. There would be no more discoveries waiting, no new patterns to uncover, no hidden connections left to explore. Knowledge would become static instead of evolving. But the universe doesn't seem built that way. It keeps surprising us. The deeper we look, the stranger and more beautiful it becomes. It challenges our assumptions, stretches our imagination, and constantly reminds us that reality is richer than our first impressions. So the real goal isn't to reach a final explanation. It's to keep exploring, to keep refining our understanding, to keep listening for that deeper harmony beneath the noise of everyday experience. Mathematics gives us a way to hear that harmony more clearly. It lets us translate nature's patterns into something we can grasp, test, and share. When you look at the world through that lens, everything changes. A falling object becomes a clue about gravity. A beam of light becomes a story about waves and particles. Even the passage of time becomes a feature of geometry rather than a simple ticking clock. The ordinary transforms into something profound, because behind every event lies a structure waiting to be understood. And the remarkable thing is that this search belongs to all of us. You don't have to be a physicist or a mathematician to take part in it. All it requires is curiosity, the willingness to look at something familiar and ask why it behaves the way it does. That simple question has carried humanity from watching the stars to walking on the moon, from counting numbers to probing the fabric of space-time itself. So don't think of mathematics as dry symbols on a page. Think of it as the key that unlocks hidden patterns in reality. Think of it as the bridge between thought and nature. We may have invented the symbols, but the truths they reveal were always there, waiting to be noticed. The universe is still playing its grand game. The pieces are still moving across the infinite board. We may never learn every rule, and we may never see the whole picture, but we can keep watching. We can keep learning. And most importantly, we can keep asking, because the more we ask, the more we discover. And the more we discover, the more we realize just how extraordinary this universe truly is.